All right. Well, thank you very much to the other Swampland organizers for inviting me to speak. Today, I'm going to talk about some work I did along with Jonathan Heckman, Jake McNamara, and Julio Parra Martinez. And so, part of kind of the motivating, kind of the base motivation behind this work is to understand string theory in non-supersymmetric settings. So I would say a central goal of our community is to understand non-supersymmetric backgrounds better, both conceptually and quantitatively. So this is both a question of exploration, i.e., what are the set of consistent non-SUSY vacua, and the two general types of non-SUSY vacua one can consider, at least tachyon-free. So one could consider, for instance, non-SUSY strings. So for instance, in 10D, there's three known tachyon-free non-supersymmetric string theories. And one could also consider non-supersymmetric compactifications of 10D superstrings or M theory. And one can do this in a number of ways by including some fluxes or some Church-Fork spin structure. And this is also a question of computation. So can we calculate non-perturbative corrections even when SUSY is spontaneously broken or explicitly broken? So in particular, one big question we'd all want to answer is our constructions of proposed constructions of metastable de Sitter vacua well controlled. So a kind of simpler version of or kind of a more specific version of this question was asked in at the Strings 2024 conference. So at the time, they collected, around 100 or so open questions. And one open question that's going to be relevant for us is, how do we classify all possible branes in non-supersymmetric string theory? So this is a simpler question than full generality of non-SUSY branes and non-SUSY string theories, but it's a seemingly simple question that we don't yet have the answer to. And some of the progress towards this direction I'm going to review a little bit today. And also, this question is especially relevant because this was asked by the current speaker. Yeah. So just to briefly review the kind of old non-BPS branes and string theories, this dates back to the 90s. So these are non-BPS D branes. And being D branes, they had explicit worldsheet CFT constructions. And some of which are stable and some of which are unstable. So in particular, the type 1 D0 brane is a stable brane, which one can argue from many points. From the worldsheet, the clearest way to see that is that there's no open string tachyon for this configuration. One can also consider, for instance, in type 2b, D2p branes, where now this is the BPS branes have a odd number here, but when you put an even number there and impose Dirichlet boundary conditions, these branes will have an open string tachyon and will decay. So some more newer non-BPS branes that have been discovered / proposed in string theory. So one example or set of examples are so-called R7-Branes, which are characterized, which one set of them are characterized by having a monodromy associated with a -1 to the FL gauge symmetry. So for instance, in type 2b or type 2a, this -1 to the FL, where FL is left-moving space-time fermion number, acts by sending D branes to BPS D branes to their anti-branes. So in these papers, we discussed several interesting properties of these objects. And another kind of set of new non-BPS branes are housed in heterotic string theories, And so namely, for instance, there's a 7-brane there associated with in the E8 string associated with permuting the two E8 factors as you go around the 7-brane. And also there's kind of rediscovery of older work where the 0-brane in SO32 heterotic string was also proposed earlier by Polshinsky. And also there's some recent work by this group here on understanding the tensions of some of these objects. So most of this kind of uh, newer non-BPS branes, they're sort of motivated by the cobordism conjecture. So what the cobordism conjecture is in a nutshell is that if I have, let's say, quantum gravity with some asymptotic boundary or part of the asymptotic boundary, I'll call MK, where K refers to the dimension of that boundary, along with possibly some flux data or some other stringy data associated with those boundary conditions, then I must be able to always fill in this background by some dynamical objects in the quantum gravity theory. And this is necessary in order to, or what these authors show is that this is necessary in order to not have global symmetries in quantum gravity. So just as a very simple example, if I have as my asymptotic boundary some 8 minus p sphere with an RR flux, with non-trivial RR flux on it, then the thing that kills the cobordism class there is a DP brane. That's fairly simple. And in particular, if one considers this cobordism conjecture when K, the dimension of this manifold, is 0, this implies that there must exist domain walls of finite tension connecting all string theory vacua of the same dimension, or more generally, all quantum gravity vacua of the same dimension. Uh, yeah, perhaps more conservatively. And there was also an earlier work by Disselfort, Fried and Moore, which mentioned briefly that there may exist some domain wall between type 2A and type 2B. So today, what we're going to do is we're going to explore, we're going to take this cobordism conjecture seriously and propose the existence of a finite tension 2A, 2B wall and try to understand what its implications would be on worldsheet physics. So for instance, we'll think of these as so-called GSO defects, which I'll make clear going forward, and also bulk implications of such a domain wall. Okay, so just a brief outline. We're going to first discuss what this domain wall would look like from the worldsheet. And before discussing the bulk physics and also some implications on the stability of the previously mentioned R7. Okay, so what we're going to do today is consider an F1 string going between the domain wall separating A and B. And it's important to emphasize that we're not going to treat the F1 string, we're not going to do perturbation theory in the F1 string. How we're going to think of this situation is an F1 string as some long probe with some effective field theory on it, and then some defect separating the two sides. So here's a kind of a worldsheet illustration where on one side of the worldsheet we'll have type 2A, on the other side of the worldsheet we'll have type 2B. Tau and sigma are worldsheet coordinates. And in the middle, we'll have some a priori unknown deformation of the 2D CFT. But what we're going to be concerned with is extracting kind of universal features that such a 1D defect in the worldsheet CFT should have, and then try to extract some statements on bulk physics from this as well. So just to review, just the type 2 worldsheet. So working in RNS formalism, the action looks like this. So I have some bosons. Mu parameterizes my spacetime coordinates, and I'm going to have some left and right moving Majorana vials. Here's an illustration of the worldsheet. And what we're gonna do is we're gonna restrict to light cone gauge. So in particular, we're gonna fix some of the light cone worldsheet sigma model coordinates, and we're gonna be left with a CFT, which just to focus on, for instance, the left moving piece, the right moving piece will essentially be identical. We're going to have 8 chiral bosons corresponding to the tangent directions to this heavy string in light cone gauge, as well as 8 worldsheet Majorana vials. And of course, just as review textbook material, the R sector will correspond to the fermions having periodic boundary conditions. The NS sector will have anti-periodic boundary conditions associated with the sigma direction. Okay, so again, just restricting to the left moving sector of the CFT, the NS sector, recall, has a tachyonic ground state due to the negative Casimir energy, and type 2A and B string, although to get A or B, I'll describe in a moment the difference between the two. But to get either one of them, we impose some GSO projection, which projects out, in particular, the NS tachyon and half of the R sector ground states. In modern language, the GSO projection corresponds to the gauging of a Z2 symmetry, which is generated by left-moving fermion parity. Left-moving because we're restricting to just the left-moving CFT. And notice, just to emphasize, lowercase f will refer to worldsheet fermion number, whereas capital F refers to spacetime fermion number, both left moving in these cases. Okay. So an equivalent way of understanding this is summing over spin structures on the worldsheet. And there's an interesting subtlety related to backfiring bosonization. I won't have time to discuss it here, but we discuss it in our Appendix A. And also see some more recent work by these authors for higher dimensional versions of the subtlety. Okay, so what is GSO in a nutshell? So again, restricting to left moving sector, my partition function for my type 2 string will be for the left moving piece will be some sum over on a 2 torus will be some sum over spin structures, right? So each of these pieces are, some powers of theta of theta functions divided by, some fourth power of eta functions, which is textbook material, and the general sum looks like this. But I see. Okay. But there's an interesting difference between each of these spin structures. So here, what I'm illustrating is so I have a 2 torus here, and A refers to anti-periodic boundary conditions. So the spinner, so AA, and then corresponding P is periodic. When I consider modular transformations, what will happen is I'll permute these three amongst themselves, and this will permute to itself, the periodic one. And the key kind of conceptual difference between these different spin structures is whether or not the number of zero modes of the Dirac operator is 0 mod 2 or 1 mod 2. So in other words, if I just try to solve the Dirac equation on a T2 with periodic boundary conditions, I'll necessarily have some 0 mode. And so that means, means that this ARF invariant. Oh, did someone have a question? Okay. That means that this ARF invariant will be 1 mod 2. Just by definition, and then if there are no 0 modes, then the ARF invariant will be 0. And this another kind of nomenclature is that one calls these three spin structures even, and this spin structure odd. And this discussion, and I'm specializing in T2 for simplicity, but this discussion generalizes to all Riemann manifolds, where even spin structures will get permuted amongst themselves under modular transformations, and likewise odd spin structures will. And of course, these ARF invariants will be invariant under modular transformations. Okay, so what does this amount to? Are we going with this? Going with this is that, so I mentioned earlier that the GSO projection can be thought of as a Z2 gauging of this symmetry. And in associated with the Z2 gauge symmetry, one can add a theta angle. So in other words, as I sum over spin structures, I can include a weight theta L, which adds signs depending on whether I have an odd spin structure in my summand or not. And to give a kind of analogy with 40 Yang mills, if I have, I can include a theta angle for 40 for this gauge theory as well. This time, the instanton density is now an integer instead of something that's Z2 valued. And my theta can be some continuous parameter. And the analog of a Yang-Mills instanton on some four manifolds will be this odd spin structure on sigma 2. Okay. Any questions so far on this? Okay. So going back to the sum, if I have theta L equal to 0 mod 2, then I'll get the sum I wrote before. And if theta L is 1 mod 2, then I'm going to alter this by a sign. I'm gonna weight the periodic spin structure by a sign. And so when I consider the partition function for string theory on this amplitude on this T2, really I should combine the left moving pieces with the right moving pieces. This is why I wrote theta L here. And if I consider, for instance, some sort of, well, let me back up a bit. Yeah, I think I got ahead of myself. So yeah, so theta L is going to be 1 mod 2. And then if one considers some sort of interface on the world sheet separating a region which has theta L is equal to 0 mod 2 and theta L is equal to 1 mod 2, then what this means is that I have some 1D theory living on this interface, and its anomaly theory is this ARF 2D topological field theory living on this side over here. So what this ARF TFT is doing is it's just a kind of invertible topological theory that's just weighting that just the partition function of it is just -1 on odd spin structure manifolds and +1 on even spin structure manifolds. And there's a old theorem, essentially, I think due to Lieb, Schultz, and Mattis, that one must have a 1D Majorana fermion living on this interface in order to cancel this anomaly. So one has some sort of symmetry and forced gaplessness on this boundary. And in its matter theory literature, this is known as the fact this is known by as having, if one has a Kataev chain and if one imposes a boundary, then that boundary must have some gapless 1D mode living on it. And there's another way to think about this situation in terms of having a massive fermion, a 2D fermion on this side with negative mass, and then a domain where it changes from negative to positive, and then in the middle it has some massless mode trap there. Okay, so now one combines the left and right sectors. If one has theta L and theta R not equal to each other, then one ends up with type 2A, and then one can check again. This is just standard textbook material that if these theta angles are identical, then one ends up with type 2B. Okay. So now putting it all together, if we have on the world sheet some sort of interface separating type 2A and type 2B, that means that I have some theta angle here, which is given by this component 1 comma 0. And over here, for instance, I'll have 0 comma 0. So this means that I'll necessarily have some 1D fermion living on this defect. Okay. Equivalently, type 2b can be seen as an orbifold of type 2a by gauging -1 to the capital FL and vice versa. So this defect can also be seen as a half-space gauging interface. So let me go back. If I have some global symmetry -1 of the FL on type 2a over here, and if I decide to gauge that global symmetry just on a half space, I'll end up with the type 2b on this side. So if one isn't familiar with this orbifolding, essentially when you gauge by -1 of the FL, you'll project out by all the left, you'll project out the left moving Ramon sector, and then of your initial theory in type 2a, and in this example I stated. And then your twisted sector will be the the left moving Ramon sector of type 2b. Okay. So there's two important worldsheet properties of these interfaces that I want to highlight. So one is that if one now considers a boundary to the worldsheet, so that's this what I've written in black here, and then sticks this interface in the middle, then it was, so if one has a boundary condition here being the non-BPS dp plus 1 brane in type 2a, then because, as Sen showed in several papers around this time, that if one gauges this non-BPS D brane by -1 of the FL, one obtains a BPS dp plus 1 brane on the right-hand side. So from the perspective of the worldsheet, that means that this boundary condition in type 2a will get mapped to this boundary condition in the 2b worldsheet. Okay. And additionally, another consequence of this interface being related to a half-space gauging is by the fact that if I have some topological symmetry operator U associated with -1 of the FL on the type 2a side, then the symmetry operator can terminate on this interface simply because if I view the right-hand side as summing over all networks of these topological symmetry operators U, then I'm free to just include this operator as just as basically yeah, it'll basically dissolve on the right-hand side once I sum over all networks of this operator here. And similarly, one can make the identical statement for the -1 of the FL symmetry operator for type 2b. Okay, so
Can
now
I ask you a
to,
question?
sure.
Yeah. I'm a little bit confused, and to make sure, for the quotient, is the FL, it means the fermion of worldsheet or of the spacetime?
Yeah, it's the left moving space-time fermion number. So it's so what it does, so what it is it's just basically under this Z2 symmetry, all left moving Ramon states are odd.
Okay.
That's how it's defined.
Uh, in previous page, the sense construction, the FL is for um, spacetime or worldsheet?
Space-time.
Both
Well,
for
it's
spacetime.
well, no, it's a world sheet gauging
Mm-hmm.
-1 of the FL. Yeah, so yeah, it's a world sheet gauge.
So the gauging in these two pictures means slightly different, right? I mean, in
Slightly
this page
different.
and the next page, the -1 FL means different thing.
Wait, no, it's the same thing. I mean, these lines are different. This line here is a topological symmetry operator, but this line up here is a boundary to the 2D CFT.
Okay, thank you.
Yeah. Okay. Yeah. Yeah. Please let me know if you have any more questions.
Excuse me, I have a question.
Yeah. Hmm.
So on the right hand side, you have the black dashed line in the next slide.
Hmm.
In the next slide, where you have the
Okay.
yeah, the dashed line on the right hand side. That's not a symmetry generator, right?
That is a symmetry generator. That's the symmetry
So
generator for -1 of the FL in type 2B, which is distinct, which is not the same as -1 of the FL in type 2A.
in some sense, what you have is on the left hand side, you have type 2A, and you are half gauging on the right hand side, and this D is like the domain wall between them. So on the right hand side, is that a quantum symmetry generator?
Yes,
Quantum.
that's right. Yeah, yeah. You can think of it. You can think of that as the quantum symmetry if you consider the right-hand side as a half space gauging of -1 of the FL 2A. Yeah.
So in that case, the arrow on the previous slide, shouldn't that be both ways? You have it only one way. So shouldn't the correspondence?
Oh, sorry. The arrow, yeah, the arrow, I mean the arrow is just the way to kind of that's just kind of illustrative in terms of how Sen argued, or what Sen's argument is starting with a non-BPS brane and then gauging by -1 of the FL and getting a BPS brane. So that's why I drew the arrow like that. But one can remove the arrow, and because it's not really, it's meaningful for the argument, but not for the physical setup. It's just to say that, okay, I have this CFT world sheet CFT boundary, and then the boundary condition will change from a non-BPS D-brane to a BPS D-brane as I go across this blue domain wall.
Okay, thank you.
Yeah. Okay. So now to discuss some bulk properties of the 2A to B wall. So I need to include some quick background before going into this is if one has, for instance, a BPS brane and its anti-brane um, on top of each other, the low energy degrees of freedom is so in particular, I'm going to single out the massless and tachyonic bosonic spectrum. So this will include a U1 times U1 gauge theory with its associated potentials, and will also include a bifundamental complex tachyon, I'll call TC. And um, if one considers a kink configuration for this TC, then one can produce a lower dimensional non-BPS brane. And in this non-BPS brane, it'll have a single U1 gauge theory with the gauge field given by a linear combination of the gauge fields of the brane anti-brane system. And one can show just the world sheet computation that there's a neutral real tachyon TR, which is related to TC by just taking the real component. There's also some massive scalars having to do with the uh, with normal fluctuations of the brain, which won't play a role for us. Okay, so just this reviewing this material. So if the D brain, so looking at this world sheet picture over here, if one sends a D brane through a wall, it's going to kind of look like this. So now I'm kind of drawing space-time. So here in type 2A, I have some BPS D2K brane. And the other side will be some non-BPS D2K brane in type 2B. And this D brane over here will have some open string tachyon associated with it. So now I'm just illustrating the tachyon decay on the right side. This configuration will decay to some dilute configuration, and one will essentially end up with just a BPS brane ending on the 2A to B wall. So what one can conclude is that BPS branes can end on this AB wall. So an interesting kind of side effect of this property is that if one measure is this kind of correspondence between the RR flux on one side and the RR potential on the other. Um, so this correspondence I'm going to argue for in what follows. But what this implies is that in this configuration I just said, I changed the degrees of D-brane for convention's sake. And if one has the BPS D-brane over here and measures its flux, its RF flux is just going to be 1, just by definition. And what this correspondence will imply is that if one measures the RR potential on this side, it'll be 1/2, which is a little surprising, or at least it was surprising to us at first. And one way to understand this, is that basically, if one takes this at face value, this integral of c is equal to 1/2, this implies that the non-BPS D-brane on the right-hand side of the AB wall is basically a flux brane configuration. Flux brane because it's a generalization of a flux tube one may be familiar with from gauge theory. And a related comment before going into the argument for this this correspondence is that the real tachyon is odd under -1 of the FL. So this means that the real tachyon at the AB wall is going to be set to 0. So I have some tachyon here, and that value of the tachyon is going to be 0 at the AB wall. Okay. So then what I want to argue for, I'm just going to jump to the end and then I'll review the argument. What I want to argue for is that when the real tachyon is 0, this implies that the integral of the Ramon-Ramon potential in a sphere surrounding it, linking with it, is going to be 1/2. So the argument for this starts as follows. So if one starts with a non-BPS brane, so here I'm in type 2b, so this non-BPS brane is 6 minus 2k is even. If one considers a kink configuration for this real tachyon, then one produces a BPS D brane in the middle. So it's going to be along some spacetime coordinate x1. And what I've drawn here in orange, so purple is the location of the BPS D brane. What I've drawn here in orange is the tachyon profile. So this is the vertical axis is the real tachyon value. And given that I have some BPS brane here, this means that if I evaluate the RR flux along this sphere, I'm going to get 1, which I could trade off as saying that the change in the Ramon-Ramon potential as I go from 2k plus 2 spheres, so that's going to be this black circle here. And if I drag that to the right, the change in this integral of the Ramon-Ramon potential is going to be 1. And because this whole configuration just becomes a BPS D brane in the middle, this means by symmetry that at the BPS D brane I'll have integral of this C of this potential being 1/2. And that's precisely the location where this tachyon value is 0. So then going back to this configuration, then I can conclude that, okay, because I have some BPS brane and then it spits out on the other side some non-BPS brane with the tachyon initially set to 0, tachyon value initially set to 0, then I have this kind of flux brane configuration. So what does this all mean? What's the kind of importance of this? So what's interesting is that this correspondence between the RR flux and the RR potential, RR flux on one side and the RR potential on the other, answers a conceptual question related to the discrete remnants of the RR fields. So if one considers, for instance, periods, RR periods that are 1/2, these are going to be invariant under -1 of the FL, because I can just do a large, 1/2 will go to -1/2, and then I can do a large gauge transformation to get back to the original value. So then the question is there a Z2 gauge field in the other type 2 theory after orbital folding by minus 1 of the FL. In an appendix, we proved this property relying on a mathematical statement due to T. and Hopkins that if one considers basically this K-theory spectrum, that's kind of the fixed points, the homotopy fixed point to this K-theory spectrum with respect to this minus 1 of the FL, then one gets the K-theory spectrum essentially shifted by 1 degree. What all that abstract statements mean is that K-theory classifies, for instance, D-branes, in type 2, and or in type 2b, I should say. And then in type 2a, sigma or the shifted K theory will correspond to the charges in type 2a. So this is just the statement that if you say K theory classifies charges in type 2b, then because you get a shift because the dimensions of the BPS operators in type 2a are all shifted by 1. And also I should point out that there's some related work which actually for which there actually are honest Z2 gauge field remnants. So what we're essentially showing is that in type 2, when one does this orbifolding, one may think one has a Z2 gauge field, but in fact, that Z2 gauge field is in some sense already a part of the Ramon field strength of the other theory. So one does not get an honest Z2 gauge field remnant. Okay. So now, so any questions on this part? Okay. So now I want to discuss the relations to R7 stability. So now just discussing the R7-Brane on its own, one can use a similar logic to the argument for the stability of these new non-BPS heterotic branes, as done in this paper. So the argument there essentially is that there's no candidate configuration of lower energy for the R7-Brane to expand into, at least no semi-classical configuration that exists. So this is due to the fact that the R7-Brane is Z2 charged under a gauge field. And moreover, the monodromy associated with it is not a subgroup of a continuous group. So in other words, it's not some Higgsing of, let's say, some continuous U1. And one can go beyond this reasoning by considering how an R7 would resolve from the perspective of a transverse string probe. So let's say in white, I have my F1 string worldsheet, and let's say it's Euclidean, and I place it on a transverse R2 to the R7-Brane. What this is going to produce is some Ramon local operator. Yeah, and okay, it's going to produce some local operator which is attached to some symmetry operator for -1 of the FL in type 2b. So I'm calling this RR subscript A because this can be seen as an RR local operator or vertex operator in the type 2A theory. And because if I'm in type 2b and I do a full space gauging to go from type 2A to type 2b, this operator will become non-genuine. So if one were to resolve this operator in some manner, what this will necessarily do is produce some little bubble where I have type 2A in the middle and some domain like this. So what we don't understand is how thick, for instance, this domain might be, this deformation on the CFT worldsheet. But I'll produce some region where I effectively have type 2A on the worldsheet. So if one considers the space-time perspective of this procedure, it looks like I have, if I have the R7-Brane and if I were to resolve it, in some manner, then the lowest energy configuration one would have is a type 2A to B wall on some sort of cylinder. And because this wall has some finite tension, energetically it'll want to collapse. Um, and so that's kind of a slight refinement of this kind of semi-classical intuition by Kaidi Tachikawa Yonakura on arguing for the stability of the heterotic branes. Okay, so a lot of
And
this.
one question. So why do you need to argue for the stability? Like if it's long-lived, I mean, in the end, you can always have this wall between type 2A and type 2B, regardless of the stability of the object. Or I'm trying to understand why it's so important. Yeah.
Yeah, how we're kind of arguing it is that if one were to consider some object with the same charge as the R7 that has some like finite radius, then what we argue is that the lowest mass configuration will be an AB wall with some sort of Wilson line on it, essentially. And that whole thing will just want to collapse to an R7. That's our argument for it.
Okay, so it matters that
Perhaps,
it's
yeah,
the lowest energy configuration.
yeah. Mhm. Perhaps another way to think about it is instead of a F1 string probe, one considers a D3 anti-D3 system that's probing it transversely in this type of way. And as I mentioned before, the gauge theory for the D3 anti-D3 will be a U1 times U1. And what that R7 will do is basically it'll be some sort of configuration of the gauge theory where the two U1s gets permuted. And at the center, it'll get identified with a single U1. And if I were to resolve it in some way in that region where it's resolved, I'll have a single U1 gauge theory. And that matches the spectrum of a non-BPS D3 for type 2A. So that's kind of another way to reason that, okay, well, whatever this region is, it involves this AB wall. And because this is finite tension, that thing, we'll just want to collapse.
Yeah.
Yeah. Okay. Okay. So I should mention that a lot of so in this whole talk, we've kind of proposed the existence of this AB wall and extracted some worldsheet and spacetime consequences of this. But a lot of this story in heterotic string has been known essentially since the 90s, although not quite in this language. So, for instance, if one considers heterotic SO string theory, and I have some GSO domain wall, so now I'm kind of drawing the heterotic worldsheet here. On one side, I'll have spin 32 mod Z2S, where I project out the spinor representation. And if I have some GSO domain wall, I'll basically change the global structure of the gauge group so that on the other side, I'll have spin 32 mod Z2C, where I project out the conjugate spinor gauge representation. And it's been known, and so what was known since the 90s is that if one takes G string to be very large, then this kind of property of exchanging, Z2S with Z2C is exactly the property associated with the non-BPS D8 brane in type 1 string theory. So in other words, the strongly coupled version of this GSO domain wall is something that can be perturbatively presented in type 1 language. And the analog of the R7-Brane in this context would be a D7-Brane in type 1. And this object is unstable because its associated monodromy, or its monodromy is associated with the center of this gauge group here. And because that's embedded in a continuous group, that object will want to decay. One can show by Derek's theorem that that object will want to decay because it's only codimension 2. Independently, there's on the D7-Brane, one can show that there's a open string tachyon in the 7-9 sector as another kind of string world sheet perspective to see that this object is unstable. So again, in contrast to the R7, which we now claim is stable. Okay, so just to conclude, so motivated by the Combordas conjecture, we've explored this 2A to B domain wall, and this appears as an interface separating different GSO projections, which we've explained can be seen as different theta angles associated with gauging a Z2 symmetry, and that these R7-Branes are stable, and then we've also mentioned a closely related story for heterotic slush type 1. So some future directions. So it would be interesting to actually give some non-perturbative constructions of both the 2A to B wall and the R7, perhaps using matrix theory or some other avenue. And another open question would be, since the R7-Brane is expected to be stable, is there some interacting 8D CFT living on its world volume, for instance? Another thing I want to mention is that one can also formally ask about a GSO domain wall separating the SO heterotic theory and the E8 heterotic theory, because their GSO projections, basically the thing that differentiates them is whether one separates these 32 Majorana vials into blocks of 16 or not. So one can consider a GSO domain wall for these theories as well. And also, one can ask, what are some possible pheno applications of including R7-Branes in compactifications, wrapping some manifolds, and in particular, could one consider so-called Alice strings and gauge theories, where as you go around this string in 4D gauge theory, you act by some charge conjugation. Could you construct some objects using R7 compactifications? That concludes what I have to say. Thank you very much.